so we're going over, what number was this again, Grace? Homework
Oh, and it's number 29.
29. Okay. So this is 29 from homework 34. So we're taking the derivative of inverse cosecant of secant x. This is our kind of formula, if you will, for the derivative of the inverse cosecant. So the du is going to be, the negative du is going to be the negative secant tangent, since that's the derivative of secant. And then we're going to have the absolute value of secant. And then we'll get inside the radical secant squared x minus 1. Does that look okay so far? I think secant squared minus 1 is an identity. So my guess is we can simplify that. So let's go searching for an identity. And it's going to come from our favorite trig identity, sine squared plus cosine squared equals 1. So since secant has cosines in the denominator, if we divide by cosine squared, we can create an identity that involves secant squared. So sine squared over cosine squared is tangent squared x plus 1 is equal to secant squared x. So sure enough, if we subtract that 1 to the other side, we can see that the secant squared x minus 1 is actually tangent squared x, which means we can replace this secant squared x minus 1 in the radical with a tangent squared x. That makes sense so far? Now you're going to be a little bit careful. So now we can say the square root of tangent squared x is absolute value of tangent of x. So it's not just tangent because that's a principal square root, which is a non-negative square root. So we're going to get a negative secant x tangent x over the absolute value of secant x times the absolute value of tangent x, or if you like, you could throw those into the same absolute value. That's just kind of a matter of personal preference. I'm trying to think, can we do any more? Let's see, where is secant positive and where is tangent positive? I got to think for a minute. So we know in quadrant 1, secant and tangent are both positive, right? In quadrant 2, tangent is going to be negative, and secant is going to also be negative, right? So the product of secant and tangent is going to be positive also. In quadrant 3, everything's negative. No, secant is negative, but tangent is positive. So I think that's going to goof us up. And in quadrant 4, tangent is negative, but secant is positive. So whatever we get has to, I'm trying to think if we can cancel anything there.
Don't we restrict the domain on
I don't think,
trig functions?
well, not really. I mean, we can't let it be 0 in the denominator, which is going to be, since they both have cosines in the denominator. And that's generally, unless they ask for it, we'll just do it without saying, understanding it. So we don't have to actually say that. Because even the original functions, right, secant and tangent were defined at when, well, that would be when the denominator is 0. So tangent also wouldn't work when sine is 0. Yeah, but I don't think we have to really worry about that unless they ask for it. Let's see. So our result is going to always be positive in quadrant 1 and 2, and always going to be negative in quadrant 3 and quadrant 4. I just don't think there's any good way. I think we just have to stop here. And I don't think we can cancel anything there. Or, well, let's see. Because I think, well, I take that back. Because secant is going to be positive in quadrant 1 and 4 and negative in 2 and 3, right? So, and it didn't do that.
Sounds good to me.
Yeah, I don't think we can do that. I think we have to just stop there. I don't see anything we can cancel.
Can you do 49 on homework 34?
49?
Yeah. I think we did a problem similar to it yesterday, but I forgot.
Okay. Do you know what it is? Or?
X equals 2 sine t, y equals 2 cosine t, and then find the derivative at t equals 3 pi over 4.
That's,
Or find the slope of the tangent line at t equals 3 pi over 4.
okay, yeah. So slope of the tangent line is the same thing as dy dx. And to get dy dx, we're going to take dy dt over dx dt. Does that seem reasonable?
Yes.
So let's see, so dx dt, we're gonna just differentiate that. So that would be 2 cosine t. The dy dt is gonna be negative 2 sine t, does that sound right? So the dy dt, negative 2 sine t, over dx dt, the 2 cosine t. And we cancel the 2's, keep the negative, and sine over cosine. I guess to evaluate, we just want to evaluate. It might be easier to leave it as sines and cosines. So let's cancel the 2's and say it's going to be a negative sine 3 pi over 4 over cosine of 3 pi over 4. I'm going to not use equals. I'm going to say arrow. So we don't want to say two things are equal unless they're always equal. Sine of 3 pi over 4 is, yeah, and it's a square root of 2 over 2, and because of that negative, we'll call it negative 2 square root of 2 over 2, and cosine 3 pi over 4 is a negative square root of 2 over 2. So it looks like the slope is going to be 1. Okay.
Thanks.
You bet. Kieran.
Could we do 29 from homework 32, specifically part C?
29C from homework 32, did you say?
Yeah.
Do you know what that problem is?
No, I don't say.
And could you what page is that on?
170.
What is it?
170.
170? Okay. So 170. And 29C. So 29 says f of x is cosine x plus 3x. Does that sound right? Cosine x plus 3x. And part C is saying find f inverse at 1 and f inverse prime at 1. Does that sound right?
Proceed, yeah.
So this is the challenge. Are they restricting the domain here? No, we'll be okay. Yep, because of the 3x. So cosine itself is not a one-to-one function. So you have to restrict the domain there. But because the 3x, it's kind of weird, but it's going to make it kind of wind and go up. So it will be one-to-one. So it is invertible. So if we want to find first what is f inverse of 1, this is going to be a calculator active problem. We're not going to be able to do this on our own. And then we're going to try to find f inverse prime at 1, which is really strange notation. So to find f inverse of 1, we want to input 1 into the inverse, but we can't come up with a good inverse for that. So what we're going to do instead is use this as an output for f and solve for the x. So to find f inverse of 1, we're going to say 1 is equal to cosine x plus 3x.
Okay.
So so this is like an input value for the inverse is the same as an output value for the original function.
Okay.
If I can solve for the input value on the original function, that will be the output value that we want here. Does that make sense?
Yes.
Okay, now that is not an easy problem, and we could do it, I mean, there's two ways you could do it. You could call this y1 and this y2 and find their intersection. I think it's easier if you just subtract it and make it equal to 0, and then use your, find the 0 on your calculator, which then you're just looking around the x-axis. Otherwise, sometimes you have to do a little bit of hunting on getting the window to find where the curves intersect. This one I don't think is going to be too big a deal, but because they don't get very big very fast. But, so we're going to do this, okay? So we grab our calculator. I'm not going to turn the screen, so too bad if you're at home. You have to do it on your own to visualize. Did I say that out loud? I'm sorry. So go y equals, and I'm going to clear that one off. I'm going to go cosine x and plus 3x and minus 1. And I'm going to choose for a window. I don't think we have to go very far, so I'm going to go maybe -5 to +5 on the exponent x to max and make the tick marks every 1. And I'm just going to go -1 to 1 on the y, because I just want to see where it crosses the x-axis, because that's going to be our answer. So when I graph that, there it is. Ooh. Almost looks like 0, doesn't it? Oh, it is 0. All right. We knew that, because cosine 0 is 1, 3 times 0 is 0, 1 minus 1 is 0. Well, that's kind of anticlimactic. So x is just 0. So that means that f inverse of 1 is 0. Okay? So now we can find the derivative of the inverse. So I don't know what the inverse is. I'm going to call it g just for notation purposes. Because then we know that f of g of x, f of f inverse of x is equal to x.
Yeah.
So then if we take the derivative, we'll get a chain rule derivative. Derivative of the outside function, leave the inside function alone, times the derivative of the inside function is equal to the derivative of x. This is what we really want, is the derivative of the inverse. So I'll divide the other stuff over, and this is our formula for the derivative of an inverse function. Okay, tell me if I'm going too fast. So this now, we want to evaluate at 1, which means we're going to get 1 over f prime of g of 1. This is generally the hard part to find. What is g of 1? And that's what we just said was actually 0.
Okay.
Is that okay?
Yes.
Now, we still got to find f prime, but that's not very hard, because we know that f prime is going to be a negative sine x plus 3. And so f prime of 0, I think that's what I wanted, is negative sine of 0 plus 3, which is 3.
Okay, I see how that.
Does that make sense? We didn't get to an example of one of those on the actual classroom video, but that's taking us back. Those are hard because you just don't do them very often. And it's a little bit winding path to figure out how to get there. In general, the hard part is trying to figure out what the inverse is at that particular value. Gotcha.
Speaking of ones that we didn't get to in class, on the next homework,
Ooh.
I don't have the page number, but 51 part C was the bit that you drew on the board, and then you said, oh, we don't have time, but that's the hard part. And I thought I'd be able to figure it out on the homework, but I didn't.
So
Page
can we distill all that down to what we want to try to do?
Um,
Felt like there's a little bit of a critique there. Gotcha.
178, page 178.
Page 178, 51C. Is that the question we're asking? Okay. So 51C is saying, when will, rumor spread at its maximum rate? And what is this rate? Oh my gosh. have to do all that.
I
You didn't want to try to look at that video and see where I looked it all out? No.
This one's confusing though, because in the example you gave, there was like 1 minus like e to the exponential, but this one is like adding, so it's hard to find the zero.
No, they're still adding on the other one too.
Was it?
Yeah.
I thought there was like,
Okay, no,
because I
okay,
couldn't
we can
get
do
the
this.
numerator to ever equal
2 to
zero.
the 4 minus t. So we have, well, we can do this. But I'm gonna need all my space. I got a feeling. Uh-oh is right. So we've got y equals 300 over 1 plus 2 to the 4 minus t. 300, did I say 1 minus 4 to the 2 minus t? 200. 300, 2 to the 4 minus t. Too many different ones on that page. 4 minus t. So the question we're trying to answer, that we ran out of time with on the video, is when will the true spread at its maximum rate? So what we're really trying to maximize is the derivative.
Wait, is that supposed to be 2 to the 4 minus t?
Is it? I think. Yes.
Okay.
Is it minus or plus though? Should be a plus. Okay. Let me start with the right problem. Okay? It's really hard to get good answers when you start with the wrong problem. We okay to here? Is that all right? So far?
We wrote the problem down.
What's that?
We wrote the problem down. We're
Good. Well, that's an important first start.
progress. Step 1 is a huge success.
So, okay. So we need the first derivative, dy dt. So I'm going to take the denominator times the derivative of the numerator, which is 0, minus the numerator times the derivative of the denominator. And the derivative of 1 is 0. And the derivative of a to the u is a to the u natural log 2 times du. You okay with that? So it's going to be a to the u, 2 to the 4 minus t, times the natural log of 2. And that's going to give us a negative 1 from the derivative of 4 minus t, the du. That's going to be all over the denominator squared. So a little minor cleanup. The negative makes it positive. So it's going to be 300 natural log 2 times 2 to the 4 minus t all over 1 plus 2 to the 4 minus t squared. That's our first derivative. With any questions on the first derivative that we needed to ask, or we're okay with that? So now the challenge is we're going to do the second derivative. Okay, so here we go on the quotient rule. So our second derivative is going to be our denominator, 1 plus 2 to the 4 minus t squared times, let's see, we're going to again get our 2 to the u times natural log 2 times du times that constant. So we got the numerator, so it's 300. We're going to get a natural log of 2 squared. I think I'll do it that way. And then times that same 2 to the 4 minus t, and we need a negative in there. Did I miss anything? That's a to the u times du is the negative 1 times another natural log 2 from the derivative of 2 to all that. Okay, minus the numerator, which is this 300 natural log 2 times 2 to the 4 minus t times the derivative of the denominator. Oh, yuck, now we got a chain rule. So we've got a 2 times 1 plus 2 to the 4 minus t to the first times the derivative of this 1 plus 4 minus 2 to the 4 minus t. The 1's gone. Kent, you with me here? Yeah, you look like you're hurting there. And then we get an extra negative, right? which is going to make that be a plus. We okay there? And all over the denominator squared. 1 plus 2 to the 4 minus t. Squaring the square makes that a 4. Okay. Now, a lot of this stuff isn't really going to matter because what we're trying to do is find out where is this equal to 0. Where, because this is the derivative of the derivative which we're trying to find a maximum. So we want to know where is it increasing the fastest. So we're trying to maximize the first derivative. So we're looking at where its derivative is 0, and then is it going to go from positive to negative there. So the denominator doesn't make any difference, right? Because that's not going to make this equal to 0, and this is never going to be undefined because this exponential is always positive. An exponential is always positive, so that's never going to be 0. So we can just ignore that completely. Now, in the numerator, let's see if we can do some factoring. Good grief. There certainly ought to be a lot we can factor out. So we certainly have a 1 plus 2 to the 4 minus t in both of those. So I'm going to pull out one of those. 1 plus 2 to the 4 minus t. Is that okay? So I'm going to keep track of that. That's going to take care of one of those, and we've taken care of that. For constants, we've got, it looks like a 300 in both cases, and a natural log 2 in both cases. That look right? So I'm going to go 300, natural log 2, and so that's taking care of this 300 in one of those, and that, and that. And we have a 2 to the 4 minus t in both of them. Does that? No. Yeah, we do, right? So 2 to the 4 minus t. And so we've taken care of that one and that one. And I think that's about it. Does that look okay? Let's see what's left after we've hopefully done some serious house cleaning. Still have one of these. So we have 1 plus 2 to the 4 minus t. We took out that 300. We took out one of those. There's still another natural log of 2. And I think we still have that negative sign. Does that look good? I miss anything on the first term? I think that's all there is. On the other term, we have this 2 and this 2 to the 4 minus t. I think that's it. Plus 2 times 2 to the 4 minus t. Are we okay to there?
I lost the negative when I did it.
Oh, is that helping then?
Yeah, because everything was above 0.
Yeah, so then you're like, you never. Yeah. Yeah, details, one little negative sign. Okay, now, these, so we have the thing in the brackets is multiplying all this stuff to be 0. But all of this stuff, that's never going to be 0. So we can just ignore that. That's not going to contribute anything. So now we're just concentrating on what's left here. And so because this one is a negative, I'm going to add it to the other side. So we have 2 times 2 to the 4 minus t, that's this one, is now going to equal the 1 plus 2 to the 4 minus t times natural log 2. I don't know if that's any help or not. I don't know. Try to solve for the t here ultimately. So I think we're going to have to bite the bullet and distribute here. We got 2 times 2 to the 4 minus t. That's going to be natural log 2 plus 2 to the 4 minus t times natural log 2. I think we're going to have to get those on the 2 to the 4 minus t's on the same side of the equal sign. And so I'm going to subtract this one over. So we have 2 times 2 to the 4 minus t minus 2 to the 4 minus t times natural log 2 equals natural log 2. You all right so far? No, we're not all right, but that's our choice. So we're going to factor out this 2 to the 4 minus t, leaving behind that 2 and that minus natural log 2 equaling this other natural log 2. That look okay? So we're going to divide all that stuff over. So we have 2 to the 4 minus t is natural log of 2 over 2 minus natural log 2 so far. I don't know where this is going, not anywhere good, I don't think. And you have to take the natural log of both sides. So we're going to get, going to bring the 4 minus t times the natural log of 2. Oh, we got logs of logs, always not what we want. Natural log of the natural log of 2 over 2 minus natural log 2. We're not supposed to get a nice answer here, are we? Or, I mean, we're not going to get like 1 or 3 or something, are we? Going to divide by natural log 2. I think there's better examples than this. Neither am I. So I'm going to add the t over here and subtract that to the other side. Is that okay? Yeah. And did they just give you a decimal answer, probably?
You can crunch it.
All right. Is there an answer in the back on that one?
I'm trying to find it. What section is it?
What section is this?
Let me know. Katya, did you ask this question? What section was it in?
Homework 32 is a part of section 3. Oh, yeah, they got 4 days.
They got more.
They literally did. No,
We might be
wrote
close,
this.
I don't know.
Yeah.
I get 4.914
Yeah.
4.994.
from the.
That rounds to 4, it's in my phone.
Alright, now we just need to
They
figure
did
out what we did wrong.
What's that?
They did round a lot in this problem.
Okay.
Because they had to round to like whole number people.
Yeah. Yeah.
Um,
We will actually talk, this logistic growth thing is, we will come back to down the road, because we're going to learn differential equations. We'll solve differential equations that lead to these. So, but it won't be quite this messy. You know, part of the problem is, you know, we'll do these with an base e, which makes it way nicer on the derivative. So you don't have all those natural log 2's all over the place. And we'll usually do it with just a negative something times t, which will make that a little nicer too.
Or we just leave all these types of problems to the wolves and.
Well, actually, there will be wolves involved in some of those problems. Yeah, actually, so yeah, we will leave it to the wolves, but not quite the way I think you were intending. Okay, well, we better hurry up and take a quiz here, right? Well,
I mean, I think I homework now that you mentioned it.
today is what, Wednesday? I gotta give it to you today.
I can come up with a few
Sorry,
more
guys.
questions.
I'm sure you could. All right.